Okay, so chapter 14 is functions of several variables. These are things that you've probably encountered already in other classes, but here we're going to talk about some of the mathematics of functions of several variables. For example, if you're in chemistry, a really common example of function of several variables is the ideal gas law. You remember that PV equals nRT thing, right? If you solve for P in that equation, PV equals nRT, you get nRT over V, right? And P depends on the temperature and the volume, right, in particular. So there are two variables that determine what P is going to be. P is a function of several variables. In this case, it's a function of temperature and pressure. And you can shift that thing around and get all kinds of different examples, but it's just, they're commonplace, they're everywhere. Any quantity that depends on a multitude of variables is a function of several variables. And it's really useful, and part of the purpose of this class is to teach you how to analyze those kinds of functions. And it's remarkably straightforward, and you know, it could have been so much harder, and you know, we're lucky to live in a universe where the analysis of these functions of several variables is actually so straightforward and really just depends on a good understanding of Calc 1 and Calc 2. It never ceases to amaze me how the topics in Calc 1 and Calc 2 lift up into this particular topic so easily. So here we are in chapter 14. Let me give you a kind of another way of looking at this or contextualizing this. Try to write on this without actually converting. So up until this point, I'm going to convert. Okay, up until this point, in particular, curves R of t are functions of one variable. They are functions of one variable, but so were the functions in Calc 1 and Calc 2. They were also functions of one variable. How is a curve different from those functions that you encountered in Calc 1 and Calc 2? Yeah, I mean, so with these curves, we were talking about you plug in a number and you get a position in space, right? And so a curve sort of traces out a shape in 3 dimensions. Nick, did you have a comment?
Well, with a function like Calc 1 or Calc 2, you plug in 1/2 of the position and you get the other half, right? Like you plug in
yeah, right.
And you get a y value. Whereas with curves, you plug in sort of
an unrelated value,
unrelated
right?
Value and get all of it.
Right. That's an excellent observation. So these are at some level different. These curves. One, because they actually, in some cases, give outputs in 3 dimensions or in 2 dimensions with a one-dimensional input. And that's the thing I want to focus on. So a mathematician might characterize the function r as mapping the real number line into, say, 2 dimensions or 3 dimensions. Okay, and the funny capital R with the superscript 2 or the superscript 3 or no superscript, it refers to the real number line. And when you raise it to a power, like the real number line squared, what do you think that means? That's the xy plane. Here's a copy of the real numbers. Here's another copy of the real numbers. Put them against each other like this, and now you've got the xy plane. R3, right? What do you do with R3? You get another copy of the real numbers, and you put it right here, and now you've got 3-dimensional space. And this is a really convenient notation for mathematicians who often like to talk about R1, R2, R3, R4, R10, R300. Okay, higher dimensional spaces. And it's It's part of what mathematicians, it's part of regular notation in mathematics. So what we've been looking at with curves are functions that take a single value t and output a value in 2 or 3-dimensional space. Does that make sense to everybody? What we want to do in this chapter is reverse that. So I want to think about a function f that goes from R2 into R. And I'll put parenthetically or R3. But mostly we're going to focus on this situation. The situation where you plug in 2 numbers and you get out a number. So it turns this function kind of on its head. Okay, just like these guys, just like curves have a very nice geometric visualization as sort of a trajectory in space, these guys have a really nice visualization as a surface in space. Let's talk about that. So we might write so such functions can be visualized as surface in R3. Okay, let's back up to Calc 1. We've got a function like, let's say, x squared. Okay, how did you plot that thing? Well, back in 8th grade or 9th grade, what you did was you took a value x, you plugged it in, you got out a y value, and that made a coordinate pair, right, x, y? And then you would plot that coordinate pair on the xy plane. And if you did that an infinite number of times, what would happen? You would trace out the curve. Of course, you didn't do it an infinite amount of times because you didn't have that much time to do it. But you would do it for enough points to where you got an idea of what the curve looked like, and then you would just kind of sweep out the curve. Okay, so x squared, you plug in 2, you get out 4, and 2, 4, right? Here's 2, go up 4 units. Plug in 1, you get out 1, here's 1. Plug in 0, you get out 0. -1, you get 1. -2, you get 4, right? And you see that parabola come out. Okay, we're going to take that same idea and do it with these functions from R2 to R. The only difference is instead of plugging in 1 number and getting out a number, you're plugging in 2 numbers and getting out a number. How do you plug in 2 numbers? You start with a plane. And you pick a value. And that's the input value. Where do you want to plot the point? Well, you plug that in to the function. You're going to get out a z value, and that's where you plot the point. So you plug in this point, and you go up to f of x, y. And this height is z. And you do that all over the place. Do it here, maybe go up here. Do it here, maybe go up here. Here, go up here. And imagine if you could do that an infinite number of times, what would be formed, or what would resolve, would be a surface that's above the xy plane, maybe in some places below the xy plane in some other places, but a surface. The process is exactly the same, and that's the thing I can't emphasize enough. The process that you generate these things by is the same as Calc 1, or same as 8th grade, whenever you learn that. Okay, what we're interested in is what can calculus, how can understanding this geometry and knowing a little bit of calculus, what can we do with this? Well, it turns out we can do quite a lot. We can maximize and minimize these functions, just like we maximize and minimize functions of a single variable. You can get a notion of concavity, right? Where is the thing sort of concave up and concave down? The other thing we're going to start looking at is sort of slices of the surface. What does a slice of the surface look like? What does a slice in the x direction look like? What does a slice in the y direction look like? And what does a slice in the z direction look like? And all three of those things have important meanings and will help us analyze these surfaces. So my goal today is really to just spend a lot of time helping us internalize this process and internalize the geometry of a surface, so that on Wednesday, when we start talking about taking limits and differentiating and all that kind of stuff, you have a really good grip on what a surface actually is. So with that in mind, let me switch over to the software that I'm going to be using most of the rest of the period here. Here. Okay. So if you look on the class syllabus in the supplemental materials section, I've got two links. I've got a surface plotter and something called a level curves plotter. I'm going to spend most of the time today talking about the surface plotter, and then I'll finish talking about the level curves plotter. These are both pieces of software that are written in Java. A lot of you guys might not have Java installed on your computers, but what should happen is when you click on this thing, it'll say something like, this requires Java, would you like me to install the plugin? And you just say yes, and then it might take a little while to download the software and install it, but just take all the default values, install Java, maybe restart the browser, I don't know, and then try to run it again. And if you have trouble, come see me tomorrow in my office hour. Bring me your computer and I can help you out. So we've got these three Java applets. We're not going to use the cylindrical or the spherical one, although you're free to play around with them, obviously. We're interested in the Cartesian one. This is the one that uses x, y's, and z's. So click on that square, and what happens is it'll launch an external program using Java. And again, you might get some warnings. You know, do you really want to run this Java program? Just say yes. Okay, and I'm not saying you should always say yes when you're using your computer, but in this case, it's okay. All right, so we've got two boxes that pop up. On the left-hand side are all the parameters that go into building the surface, and on the right-hand side is just a visualization. And you can actually click and drag around that visualization and get a look at this three-dimensional surface. What I'd like to do is walk you through not only how this thing works, but maybe some of the quirks of the software, because it is a little bit clunky, but it's free software, and you know it does a good enough job. Okay, so let's start with something straightforward first. I'm going to do something like x plus y equal, or x plus y maybe plus 1. Come on, there we go. Okay, so there's a nice plane. In fact, what it's doing, there's nothing magic going on here. What we have is the xy plane. These little bars here indicate where the xy plane is, the z axis coming straight up and down. Nothing magic going on here. Okay, this is a simple computer program. All it does is it takes the x range, which goes from -10 to 10, and it chops it up into, say, 100 pieces. And it takes the y range and chops it up into 100 pieces. Okay, and what that does is it generates about 10,000 points in the xy plane. And then it does exactly what you did in 8th grade. It starts at the first one, plugs it into the formula, figures out how high to go, and plots it. Then moves to the next one, figures out how high to go, and plots it. And since it's a computer, it can do that really fast. And it does all those 10,000 points, and when it's done, you get a surface. So no magic, right? Behind the scenes, it's just a bunch of for loops and calculations and all numerical and no magic. All right. This plane, now that we know that how it was made, what's the normal vector for this plane? Bit of review. 1, 1, I'll buy that. What was the last one? -1, how'd you get that, Hannah? Yeah, so let's look at this thing. We've got z equals what? X plus y. Was it +1? Okay. Now that's the function, right? So if I plug in x and y, like if I plug in x equals 1 and y equals 2, then what I get out is z equals 4, right? So here's x equals 1, here's y equals 2, go up, right, to 4. All right, so that's how you plot the thing. But don't forget all the stuff you learned in chapter 12 and chapter 13. This is still just the equation of a plane if you look at it in the right way. -x, -y, z equals 1, right? And now you can pick off the coefficients, and you see that the normal vector is -1, -1, 1, or 1, 1, -1, as Hannah suggested. Either one, right? Okay, let's see if we can actually see that in the surface itself. I'm not sure how well we'll be able to see that, but let's give it a try. Okay, 1, 1, -1. 1, 1, -1. So go out a distance 1 in the x and a distance 1 in the y. So if you look down from above, the normal vector is going to point at a 45-degree angle in the xy plane, right? And then what's it going to do? It's going to go down 1 unit in the z direction. So it's 45 degrees here and then down. Does that look normal?
Are we looking blue or the other?
We're looking, let me get the blue and let me get those guys out of the way. We're ignoring those at the moment.
Oh.
Okay? Okay, so yeah, we'll look down here at the xy plane, right? 1, 1 is here, and then -1 or -1 unit in the z direction. Does that look like normal to the plane? Maybe. It's hard to tell, but yeah, I mean, here's 1, 1 and then down 1, right? So maybe you buy that. It's hard to see, I admit. Okay. Let's keep working. So we've got, we can plot planes. Essentially, any equation where you can isolate z, you can plot as a surface. Right? So there are some equations where it's really hard to isolate z, and then it's difficult to plot it as a surface using this software. You can still do it, but not with this. But any equation like a plane where you can isolate z really easily, that's perfect for plotting surfaces with this app. All right, let's look at a different example here. Let's look at x squared plus y squared. So z equals x squared plus y squared. All right, let me tweak the range here so that it sort of fits a little bit better. So let's go -2 to 2. Let's go 2 to 2. And maybe make the z, I don't know, let's go -1 to 6. All right, there's the surface. It was generated exactly the same way as the plane. Chopped up the XY plane into about 10,000 points, went through and plugged them all in, and this is what popped out. Okay, no magic. A little bit, let's talk about how to interpret this. You'll notice that the axes here, the X, Y, and Z axes are floating up here in space. This applet, again, the guy that wrote this, maybe made different choices than I would have, but hell, at least he wrote it. This X, Y, Z coordinate axes, all this is really telling you is what the directions are of positive x, positive y, and positive z. That corner down there where the three lines meet, that is not the origin. That is not 0, 0, 0. Okay? You could make it 0, 0, 0. For example, if I change this to, say, minus 5, 5, then, in fact, that is the origin. But that's just another little quirk of this piece of software that I want to point out. Not to be confused. This is, generally speaking, not the origin. All it is the center of the view. Is that clear to everybody? Okay, so I've moved it to the origin by making all three intervals symmetric. Negative 2 to 2, negative 2 to 2, negative 5 to 5. When I do that, then they coincide. The center of the box is the origin. Okay, let's talk calculus a little bit here. If this is a function of two variables, x and y, what's the smallest value that I can get out of this function? 0. And where does that value occur? At the origin. So, for example, if I ask you what's the minimum of this thing, you would say 0, and it occurs at 0, 0. It occurs at 0, 0 in the xy plane. That's the way you want to start thinking about these. What about maximum? Does this thing have a maximum? It's kind of a tricky question, yeah, and that's exactly the right caveat. Let me zoom out here a little bit. In this range, in fact, it does have a maximum. It has 4 maximums. One here, 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 and here. But we know that this function actually goes on forever, right? It goes off and it covers the entire xy plane. In that context, no, it doesn't have a maximum. Okay, z is unbounded. You can get as high as z as you want. Okay, so we will start talking about things like that. What are the maximums? What are the minimums? And it turns out, as I alluded to earlier, a lot of the things we learned in calculus are going to help us find these maximums and minimums. Okay, let's talk a little bit about these guys. That thing. And this thing. I want to try to get them both going at the same time. Anyway, all right. What's going on there? These are called parameter curves. I don't know if that's the terminology the book uses, but it's as good a terminology as any. Parameter curves are curves. How do you think this blue curve is generated? Anybody have a guess? So close. The blue curve is fixing x and letting y vary. The yellow curve is fixing y and letting x vary. These are going to be two very important features of our surfaces moving forward. And they carry a lot of information about the surface. Let's look a little bit more closely at this. Let's see, let me knock this back down to 0. All right, so what I've done is I've set x equal to 0. If I set x equal to 0 and let y vary, what kind of shape is traced out there? That's a parabola. How do you know for sure that that's a parabola? Well, look at the function here. It's z equals x squared plus y squared, and I've just set x equal to what? 0. So what's left? Z equals y squared. So in the xz plane, sorry, in the yz plane, yz, I've got a parabola, just the usual parabola. And if I bring this guy back to 0, you see a similar picture. Let me flip it around this way. You see a similar picture in the xz plane. So if I fix y and allow x to vary, I get a parabola. If I fix x and allow y to vary, I get a parabola. And these cross sections help me visualize the surface. It doesn't mean that the surface might not do crazy stuff in between, right? Here's a parabola, maybe the surface is all crazy in between. But it still tells me a little bit about how the surface behaves. In this surface, we get to see the whole thing, so there are no real surprises. But some surfaces are really hard to plot, and so you might just want to look at what does it look like in the xz plane? What does it look like in the yz plane? And that's what you have going on here. And you can actually generalize this, as you may have already recognized. What if I set x equal to 1? Right, what's that cross section? What kind of curve is it? Still a parabola, shifted up 1 unit. And that's clear, right? If I, again, go back to z equals x squared plus y squared and I let x equal 1, I have 1 plus y squared, which is really just a parabola, right? Okay. Everybody okay with that notion of cross sections? That's what we're doing, is taking cross sections. All right, let's look at, all right, let's talk about this thing as a curve, and let's talk about the slope of this curve. If you were going to minimize the blue curve, where would you put the minimum? At y equals 0, right? So you fix x, and then you look at this y curve, and then you minimize that guy, and you find that it's right here at y equals 0. Okay, and that's true for any value of x. Okay, look at this now from this side. So is the minimum on the blue curve also a minimum on the yellow curve? No. Can I make it, can I slide them around so that the minimum on the blue curve is also a minimum on the yellow curve? I can if I set them both to 0. And it turns out, and this is sort of the magic of Calc 3, in particular optimization, it turns out that all I have to do is look at these two parameter curves. And if I get them to minimize both at the same time, then the surface will be minimized there as well. And that's pretty interesting given I only have to really look at two cross sections of this complicated surface. And if I can get two cross sections to minimize at the same place, then the whole surface has to minimize there. That's a really strong result. It's not something that you would a priori expect from a surface, and yet that's what you get. That's what we're going to talk about on Wednesday. So if you can find a place where these two curves are simultaneously minimized, all right, let's look at a slightly different example. I think this one will do it. That's not quite the one I want. Yeah, let me move it around, see if that helps. Yeah, I'm gonna abandon that point right now. Okay, let's keep going and talking about just graphing these things. We'll talk more about that. I'll come up with a better example for what I was going to illustrate there on Wednesday. Square root of x plus square root of y. Okay, before I pull the trigger on this thing, what's something I want to be careful about? The domain, right? What's the domain of this function that I'm about to plot? I need positive x. I need positive y. Right? I need positive x or non-negative x, non-negative y, right? What part of the xy plane does that correspond to? The first quadrant, right? So if I'm going to plot this thing, I better restrict my attention to the first quadrant, otherwise this program might blow up. Okay, so before I pull the trigger on this thing, I'm going to change the range from 0 to 2 in the x, 0 to 2 in the y. you might notice, the astute among you might notice, that this is not the function that I've got plugged in here. Another quirk of this program is whatever changes you make in the box will not take effect until you actually hit enter in the box. Not tab, not arrow keys. You got to hit enter to make it happen. Took me a while to figure that out. So if I go back here, now I'm ready to pull the trigger on this plot. Now that I've limited the range from 0 to 2 in the x and 0 to 2 in the y, now all the x and y values are safe to plug in. And the computer behind the scenes, when it plugs in those 10,000 points, isn't going to get the square root of a negative number somewhere, and it's going to be happy. Let me move those guys out of the way. All right. It doesn't look like much, but yeah, that's pretty much it. The square root of x, square root of y, plus the square root of y. Wish I could figure out how to get... not quite adept at moving this thing around. There we go. Notice that this is no longer the origin, right? Where's the origin in this picture? It's the green dot. Okay. All right. Let me blow up the z-axis a little bit so we can see a little bit more of the geometry. Okay. You know, it's got some symmetry related to it. If I look at it in this direction, right, this is looking down at this slice. I guess I'm looking at y equals 0 here. What is that shape? It's the square root function, right? Square root of x, and around this side it's also the square root function. And then this is kind of what happens when you add the two of them together in between. And if I look down from above, that's the first quadrant. That's positive x, positive y. Questions? Yeah?
So what happens if you don't restrict x and y to their domains? Does the program just say no?
Well, we can try it. I tried it in the earlier period, and it just locked up the program. But then I tried it in my office this morning, and it seemed to be fine. Like, it just only plotted the places where it was defined. So I would say it's unpredictable. But in fact, when I did it in my office this morning, it was in Linux, and this is Windows. So there might be some differences between the Java virtual machine in Windows versus Java virtual machine in Linux, and maybe, it's a little bit safer in Linux. Like the errors are the error conditions are a little bit better. But let's see. So if I back this up here to say -1, now the computer again is going to chop up the domain into 10,000 little points, and it's going to plug them all in, and it's going to throw up when it tries to plug in x equals -1, -1/2, -1/4, right? It's going to have trouble with that square root. So let's see what happens if I hit enter on this. Okay, it appears to actually have done it. And it's just not going to show me that piece of the square root function. So I don't know why it crashed in the earlier period, but so it's showing me a little bit more, right? If I look down from above, the green part exists above the positive x and the positive y, and then Java just said, I can't do it here, so I'm going to leave it blank. Okay. So yeah, your results may vary depending on what functions and domains you use. All right, so those are parameter curves. Those are the big ideas with x and y. Those are the independent variables. So if you fix x, an independent variable, and let y vary, you get this parameter curve. If you fix y and you let x vary, you get this parameter curve. And don't forget all the stuff that you learned in chapters 12 and 13. We're going to start differentiating those parameter curves to get tangent vectors. We're going to get a tangent vector along one parameter curve, and then we're going to get a tangent vector along another parameter curve. We're going to take the cross product, and we're going to get normal vectors to the surface at different places. Okay, so don't forget that stuff. It's coming back. But in the meantime, I want to talk about what happens when you fix that third variable. And that doesn't even quite make sense from what we've just done, right? Now what I want to do is I want to fix the dependent variable. Z is the dependent variable, right? And see what kind of mileage I can get out of that idea. So if I have a function consider z equals f of x, y, and what I want to do is I want to see what values of x, y satisfy k equals f of x, y, where this is a constant. Why is this interesting? The solution set here can be empty. It can be a single point or a collection of points. And it can be an infinite collection of points. And that's pretty abstract. And what I really care about is visualizing this situation. Visualizing the set of x values and y values that make the function a particular value, right? I want to know what x values and y values make the function 2. What x value, y value make the function -5. Because you'll be surprised to learn that there's a lot of information that can be had from exploring that idea. And we'll look at some real concrete applications as soon as I explore this in the software. So let's look at this notion in the software. So I'm going to switch back to the paraboloid. That's what this thing is called. It's a paraboloid because, well, if you look at cross sections, it looks like parabolas, and it's kind of 3 dimensions, so we call it oid for some reason. I don't know. Anyway, let's go back to that and back to this, and this guy. Oops, -2. And let's go here, maybe give a little bit of negativeness, even though that's not part of it. The function, and then pull the trigger on that, and okay, so now we're back to our paraboloid. I'm going to move those parameter curves out of the way. Come on. There we go. Move those parameter curves out of the way, and we've just got our paraboloid, bullet-shaped kind of thing. And you'll notice we haven't used this other guy down here. This plotter has the ability to plot 2 curves at the same time. So now I'm going to start playing around with G. And I'm not going to put sort of generic surfaces up there. Instead, I'm just going to put up something like G is equal to 2. What kind of surface is that going to be when I pull the trigger on that? A plane. Be more specific. 2 units above the xy plane, parallel to the xy plane, right? Does everybody see that? Okay. So I'll set that on. I hit enter, and that's now part of the application. And then I click this little checkbox, and that's going to turn on G. So G is the purple guy. Green is the paraboloid. And what we get to see now, or kind of get to see, is where these 2 surfaces intersect. And what's special about where these intersect is these are all the places on the function where it's equal to what? 2. What does the set of xy values for which the function is 2 look like? It's a circle. If you look down from above, it's not the inside of the circle, it's the boundary of the circle. The boundary of that circle, if I take any xy point on the boundary of that circle and I plug it into F, what do I get? I get 2. This is called a level set. for obvious reasons, right? It's level. It's all at the same height. So a level set will never look like this. It's always going to be the same height. And you can get a lot of information about a surface by looking at its level sets. And what do you, maybe not looking at one level set, but looking at a whole bunch of level sets. Like, let's go down to 1. Okay, how did things change when I went down to 1? Smaller circle. Let's go down to 1/2. Right? If I keep going down to 0, I just keep getting smaller and smaller circles, right? Okay, what if I go all the way down to 0? What do I get? I get a single point, even though the software kind of shows it as perhaps a little bit more than a point. But it really is just a single point. And if I keep going down, what do I get? I get the empty set, right? They don't have an intersection. There are no x, y values for which the function is -1. That makes sense, right? X squared plus y squared is always positive or non-negative. Okay. So those are the range of possibilities, right? I can have no solutions or no points in the level set. I can have one, or I can have a whole curve. Okay, let's talk a little bit more about specifics. What if I go back to 2 here? We all agree that this is a circle. Can you be more specific? Can you give me, for example, the equation of that circle? X squared plus y squared equals 2. Exactly. Can you tell me where the center is and what the radius is? The center's at the origin, 0, 0. What's the radius? √2. So yeah, you can get a lot of information. There's a lot of relationships between the equation of the surface and the equations of level curves. Okay. Let's look at a slightly more interesting one here. What happens if let me see if I can get a little bump in the middle here, plus 5 maybe? No, 5's too much. 1.5 cosine x squared plus y squared. Okay, so I took the parabola, the paraboloid, and I added in this extra term, 1.5 cosine x squared plus y squared. And you can see the effect that it had, right? When I plugged in 0, 0 before, right, it was down to 0. But now when I plug in 0, 0, right, this is all 0, but what happens when I plug 0, 0 into this? I get 1.5, right? I get the cosine of 0, which is 1, times 1.5. And that's where that bump in the middle is coming from. In fact, it's, yeah. There's even more to it, right? Where does all the rest of that structure come from? Let me turn off G here briefly. Come on. Okay, what's really going on is you've got this sort of like a pebble on a pond kind of thing. You've got these circularly symmetric ripples that are coming out. And then I'm adding on this paraboloid, which kind of washes them out. I'm not too concerned about that. What I want to do is play around with the level curves. So I've turned that guy on, and you see here at 2, I'm still just looking at a circle. But what do you think is going to happen if I lower this guy a little bit? I'm going to start getting more complicated level sets, level curves, concentric circles is what I'm hearing from over here. So let me knock this down to 1.5. Where's that going to put the plane? Right at the peak of those oscillations, possibly with a little bit of extra stuff built in from the x squared plus y squared, right? Okay, so if you look at that, yep, I get concentric circles, right? So this is not the best way to visualize level curves. This segues into the next application. So let me close this guy, and let's go look at the other application, which is also linked on the web page, Level Curves Plotter. Really similar interface. It's also Java. It's the same website. But hold on to your hats, because there's going to be a lot of stuff flying at you in a minute. Okay. All right, so let me turn off keep that in there, and let me try to go back to the surface that we were just dealing with, see if I can remember it. Okay, and then those ranges are probably okay. Yeah, let me tweak them a little bit. Probably have to zoom out a little bit. All right, so there's the surface. Let me zoom out on this guy. There's similar surface, and what we're going to see in this window is the collection of x and y values that satisfy the level curve. All right, so I'm going to raise this plane up, and it's going to start hitting. Okay, let's zoom out a little bit. All right, so I've raised the plane up to where it's actually hitting the surface, and it's hitting the surface in 2 concentric circles, right? And if I look down in the xy plane, if I take this point right here and I plug it into the function, what value is going to pop out? 1.5. That's the whole meaning of this geometry. Right? Everywhere along this curve, when I stick it into the function, I'm going to be 1.5 units above. Okay? I can keep lifting this up. If I keep lifting this up, you're going to see the concentric circles are going to get closer together, although you're probably going to miss it and just turn into, in fact, let me crank up the number of steps here to maybe 50. Okay, and then now we see there's a little bit of rounding error, but you see does everybody understand what's happening when I'm doing that? So up here, I'm just on the paraboloid part of it, right? And then as I go down, I start hitting those oscillations from the cosine part. And those oscillations kind of spread out and then disappear and merge. And now I'm below it, and I don't have any level set at all. Okay? Okay. Now, sometimes it's useful to not just take a single plane and move it up and down like this, but sometimes it's useful to let the computer just generate a whole set of them. Like maybe we'll just, instead of looking at each of these guys independently, why don't we put a whole bunch of them on the screen and color them differently for different levels? And we can do that by turning on the contour sets. Okay, and let me simplify this function a little bit so that we really get an idea of what we're talking about here. So here the computer's automatically generated a collection of level sets. And each color corresponds to a different K value, a different constant. You can see those values here. Okay, this guy is the inner circle, green. This guy is the outer circle, red. And there's a couple of interesting things to note here. For example, what do you think it means that these curves are further apart than these curves? What do you think that indicates about the surface? It's steeper there. Yeah. The rate of change on the surface there, the rate of change of the z-value is much faster away than it is down here. That makes sense, right? This surface comes in and it sort of flattens out at the bottom when it gets to its minimum. Okay. So there's a lot of information about the geometry of the surface by looking at level curves like this. This is called a contour plot. And I don't know how many it decides to make, but the important thing about a contour plot is that it's something like 0.2, 0.4, 0.6, 0.8, right? That it's a uniform step, right? You don't get the kind of information that Andy just described unless it's a uniform cut all the way up, right? Because if I went 0.2 and then 0.8 and then 100, it's kind of hard to get any information out of the level sets from that. So what's really important is it's 0.2, 0.4, 0.6, 0.8 all the way up. Then you look at those level sets and you get an idea of how constant motion kind of changes the function. Okay, let me show you some examples of this, some real life examples that you may or may not have been aware of. Does anybody know of some actual real life applications of level curves, level sets? Does that evoke any kind of applications that you've seen? Yeah, that's the big one, right? The topographic map. So if you're a hiker, you get these maps. You want to go down to the Eagle Cap or something like that, and you're looking at different trails, and you're deciding whether you want to go up this trail or that trail, right? You look at these elevation maps, and I think Google might even have elevation maps. In fact, we'll look at one of my favorite ones. Yeah, there we go. And let's zoom out a little bit. I think it's way out here. There we go, yeah. So if you go way out, I think that's the trailhead right there. Okay, and then, you know, it looks kind of boring, and then you fire up the topographical map. Come on, terrain, there we go. Okay, so there's the trailhead, and you kind of hike up here. Okay, I don't know if you guys can see that real well. Let me zoom in a little bit. Okay, 7,600 feet. So if I was able to bushwhack my way along this ridge, I would be going neither up nor downhill. I would be at a constant 7,600 feet. And when you're assessing a trail, for example, if you look at this trail, this river happens to go kind of along, right? You don't see the river crossing these lines very often, right? And that's what rivers tend to do, right? Here's a crossing right here, 5,400 feet. Let's keep going. Keep going. Keep going. There's a river crossing at 5,600 feet. So that whole stretch, right, from here up to here, I only had to climb 200 feet. As opposed to, let's walk from here to here, right? There's 200 feet. Okay, or from here to here, that's 200 feet. So you get a really good idea of how steep the terrain is and why the trails are where they are and where the rivers are. And you can imagine that this little stream right here is probably a pretty quick stream in the spring. This guy here is probably pretty quick too. Okay, but this guy's probably relatively slow. Okay, there's other places that you see these kinds of maps. Any other applications that you may have thought of? No? Okay, so you probably looked at this your whole life and never really thought about what was going on here. This is a pressure map of the United States right now. And if you follow one of these lines, the pressure along this line is 1017 millimeters of mercury, 1017 millimeters of mercury. If you follow this line, it's 1016, and so on. I don't think these lines are uniform. They might be. 16, 17, 18, 19. Yeah, so I think each line is separated by a millimeter of mercury. So one particular curve, one particular level curve, corresponds to one particular pressure. But when I look at all of these guys together, I begin to infer some interesting things about the weather in the United States at this particular point. For example, if I'm trying to fly a kite, do I want to be here or here? In the south or in the north? I want to be in the north where those bars are close together, because what does it mean for those bars to be close together? It means that the pressure here is much different than the pressure here. Okay, and we can actually look at this thing. We see here's 1016, here's 1006, here's 1004, right? So which way is the wind blowing in this region right here?
1016 to 1004.
It's blowing from 1016 to 1004. Almost. What's a complicating factor? Coriolis, exactly. So the Earth is spinning, and so the wind wants to go that way, but the Coriolis effect is kind of making it go in different places. But for the most part, it's a pretty good predictor of which way the wind is blowing. So you can generally guess that the wind is kind of going to be going from here to here, but it might be kind of going this way or this way, depending on the Coriolis effect. Okay? So whatever direction the wind is going, you can bet for damn sure it's going to be windy there. That's a fact. And it's not too windy here right now. Okay, so that's another application. One more, and then let me go. I want to visit WebWork a little bit, because there's some problems and they're a little bit different from what from what you'll be reading in the book. Similar, not to beat the weather drum too much, but let's look at a temperature map. Yeah, that's a boring one. It's 2006. Let's see if we can find a current one. And don't quite see the isobars here. I guess I'll go back to the boring one. So where do we see the lines of constant temperature in this map? Kind of color. Where can I guarantee, like what path can I follow to guarantee that I'll have a constant temperature? Where the borders are, right? So these are pretty broad swaths, right? And that's not quite what this is not. This is telling you when to plant trees, I think. So it's not quite right. But you could imagine that this is the temperature thing. I think there might be one. And come on, maps. And there's some isobars. Let's look at temperature, though. Current conditions, maybe? I don't know. There's a temperature map. See, everybody's kind of gone all fuzzy on me. Oh, there we go. Okay, good. So this is current temperature, 6 p.m. Eastern Daylight Time, so that's a half hour ago. And if you follow these lines here, you'll be in constant temperature. Okay. You get the same idea. Where can you get the most bang for your buck in terms of changing temperature, well, you go from here to here, right? Or here to here. There's a lot of temperature change there. That also usually indicates weather, either wind or rain or severe weather. Places where those isobars are close together are places that are of interest to weather forecasters. So this is pretty boring weather right here. It's hot, but there's not much going on there. Okay. Let's pop over to web work briefly here. And let me walk you through some of the oddities that you'll find there in the next 48 hours. Okay. So here's the first web work. It says, here's a function. Find the graph that corresponds to the following traces. So the first box is, which one is the trace for x equals 1.25? So what do they mean by trace? This is what I was calling a parameter curve. So you fix x at 1.25 and you allow y to vary. And that's going to trace out a curve, right? In the xz plane. Sorry, in the yz plane. In the yz plane. So it's up to you to figure out. Now you don't have access to the surface, or in this web work you don't. It's up to you to figure out which of these traces corresponds to which. You can take this function and literally plug it into that application, the first one that I was using. Plug in minus x star y over quantity 3 plus x star x, and plot that thing. And then you could actually set x to 1.25, and you would literally see one of these traces come out at you. And if you're really stuck, go ahead and do that. In fact, do it. You know, it's good practice. But we can actually figure out a little bit about what the answer might be without going to the plot. I say that the answer for 1 is either B or D. Does anybody see why I claim that? Nick?
Well, if you plug in the number for x, then your function becomes y times the scalar.
Yes?
So
It's a line.
Yeah, it's a line.
It's a line.
Y squared, right?
This isn't a line, this isn't a line. Does everybody see that? If I plug in a value for x, what's left is a constant times y. That's a line. So it's got to be B or D, because those are the lines. That's the kind of thinking that I want you to start developing. Okay, let's look at the next one. Similar. Next one. Okay. Even more thought-provoking, but still using the idea of trace. You're given a function, ax squared plus by, and the idea is see if you can infer what a and b are from the information given. Okay, well, the trace for x equals -1. That's where you plug in -1 here, and so f becomes a plus by, right? Can you figure out a and b from that? Okay, well, while you're thinking about that, if this is the trace for x equals -1, what variable is along this axis? Y. And this? Z. And so here, this is x, and this is z. Okay, good. A plus by, set that equal to -1. Yeah, you're allowed to use the graph here. Okay, use the numbers from the graph. See if you can infer from the graph what a and b are. I don't want an answer. Okay? Okay. Let's talk about some other ones here. This is a little more visual than the earlier examples. Come on, you can load. There we go. This is a little more visual. You kind of look at this lumpy surface. You don't have a formula for it. It's just some lumpy surface. And the idea is to use what you know about the surface, the fact this is the y direction, this is the x direction. See if you can figure out which of these traces belongs to which graph, okay, to which value. And you're not going to be able to jump over to the software because you don't have a formula for this surface. So you're just going to have to think it out. All right, let's keep going. Here's a bunch of level curve exercises. For example, let me pop up this guy. So this is like that final example that I did in the level curves applet, where we're generating a bunch of level curves for a lot of different values. For example, maybe this is looks like it's 2, and then maybe I don't know, 1.6. I can't see it, but you get the idea, right? So I've got this collection of level curves all the way down. Oh, sorry, I'm reading that the wrong way anyway. So maybe this is the level curve for like 1, 0.8, 0.6, 0.4, 0.2. Okay? What can we tell about this function and its behavior from these level curves? As you go away from the origin, it kind of levels off, right? It doesn't change as much. So what do you think this thing might look like? Set aside what the formula for it might be. What do you think it might look like?
Either go up or go out.
But there's something steep going on in here, right? And then kind of flattening out, right? And then what about, it looks like it has kind of a circular symmetry, or perhaps a elliptical kind of cross-section, right? So maybe it's a sort of a steep bump, elliptical bump that kind of flattens out. I don't know. So look at these things, see if you can figure out what's going on. Come on. Okay, the cross sections here are hyperbolas. So you got to definitely sort of remember that kind of stuff, what these curves are. These cross sections look elliptical. I don't know what. These are linear cross sections. All right, so I'll let you play around with that one. And this is just match the function with its surface. This is a nice word problem. And I think that's it. Oh no, even more surfaces. So you can grab these things and move them around, and then as long as the mouse stays in the window, it'll move. As soon as the mouse leaves the window, it stops. Okay. The goal of this particular chapter or section of this chapter is to develop your intuition about these curves. How does the algebraic expression relate to the geometry of the surface? That's the big goal. I want you to think about this hard for the next 48 hours so that we can start doing calculus on this stuff on Wednesday. Until we meet again.